How does the Carnot cycle work for heat engines? Imagine a machine that can convert heat into work with the highest efficiency possible. That's what the Carnot cycle models. It's a theoretical process that shows the best a heat engine can do. The cycle involves 4 steps, all designed to be reversible, meaning no energy is lost. The first step is isothermal expansion. Here, the working gas, often an ideal gas, expands at a constant high temperature from the hot reservoir. During this, it absorbs heat energy, but because the temperature stays the same, all that heat turns into work. Next, the gas undergoes adiabatic expansion. This means it keeps expanding without exchanging heat, so its temperature drops from the hot temperature to the cold reservoir's temperature. The gas does work during this process, but no heat leaves or enters. Then comes isothermal compression. The gas is compressed at a steady low temperature, releasing heat to the cold reservoir. Since the temperature stays constant, the internal energy of the gas doesn't change, but work is done on the gas. Finally, the adiabatic compression raises the gas's temperature back to the hot reservoir's level without heat transfer. Work is done on the gas again. When one cycle completes, the net work done by the gas equals the heat absorbed from the hot reservoir minus the heat rejected to the cold reservoir. The cycle is idealized, meaning it assumes no friction or heat loss, making it a perfect benchmark. The efficiency of this cycle depends only on the temperatures of the hot and cold reservoirs. The formula for efficiency is 1 minus the cold reservoir temperature divided by the hot reservoir temperature, both in absolute terms. This shows that no real engine can be more efficient than a Carnot engine operating between the same 2 temperatures. It also proves that some heat must always be rejected to the cold reservoir, so converting all heat into work is impossible. In real-world mechanical engineering, the Carnot cycle helps us understand the limits of efficiency. While actual engines cannot achieve perfect isothermal and adiabatic processes and face losses like friction, it guides engineers to design better engines. By maximizing temperature differences and reducing irreversibilities, we can improve performance. Knowing how the Carnot cycle works helps us see the fundamental principles of thermodynamics in action. It connects the ideas of energy conservation, entropy, and efficiency, helping us develop more effective thermal systems.